Hello and welcome to this first webinar of 2022, a new season. Today I'm going to speak about something interesting that happened in this past week. I'm going to show how we take and I took a formula that somebody wrote, an APL function, and fixed it up a bit and made it run much faster. So this is what happened. A person who is teaching themselves APL came into the APL orchard and showed an implementation of a computation in Haskell, discussed it a bit, and also showed how they had implemented the same thing in APL. And then they asked if I had any ideas for making it better. So I started working on that and discussing it with them. And the subject is something called a CPF number. It originates as a tax number, tax registration number in Brazil, but it's also used for all kinds of other purposes, kind of like a social security number or a national insurance number and so on, a people's registry. And so people have these identity cards, and if we look at it there, we can see that the number consists of 9 initial digits, those separated in groups of 3 with dots in between, and then dash 2 digits. And the way it works is that you have 9 digits, which are data digits, and then 2 digits, which are check digits, to ensure that there aren't any mistakes in data. So that's the number we're going to work with. This, of course, is a very boring placeholder number, so let's put in some random digits there that we can work with. And as I mentioned, there are 2 check digits. Those are the ones that we're going to compute based on the base digits. And the way it works is that we're first going to compute 1 digit, and then we're going to use the same algorithm for computing the second digit. So we start off with this number and break it up into individual digits. So this is a vector of integers. And then I'm going here to describe what the official algorithm is, but we're going to modify that later. We compute some weights. I'm going to come back to what exactly those weights are. Then we multiply the digits with the weights. We sum them and find the division remainder when divided by 11. And this is where the track kind of splits into 2. If this remainder, or residue, is 0 or 1, then we immediately know that the check digit is 0. It isn't 0 or 1 in our case, so we continue. Otherwise, we take that sum, in modulus 11, and subtract it from 11, and that gives us our check digit. So we take that check digit and we stick it at the end of the original 9 digits. And finally, we repeat the process again, but this time we start with 10 digits instead of 9, because we include the first check digit. The weights are a bit different. Again, we're going to come back to this. Multiply by the weights, and then we sum modulus 11, and in this case, yes, it is 0 or 1, it's 1. So then we change it into a 0. The next step we don't need, and we take that 0 and we put it at the end, and now we have our full CPF number. Okay, this is how it's described, but let's go on to the actual implementation. So we start off with the digits from the CPF number, the data digits, and the weights. Multiply them together, sum that up, 11 residue on that, and then let's give that a name. We'll call it t. This is where the branching happens. So if t is less than or equal to 1, that is, if it's 0 or 1, then the check digit is 0. Otherwise, we subtract it from 11. Now, this user that asked me the question had thought about this, and in APL it's an anti-pattern to do branching like this. Instead, we want to work on entire arrays. And so they did. They took the 0 and the 11 minus t and put them into an array together, a 2-element vector. And then they devised a clever formula to select the correct value from there. So we're using the pick function with a formula on the left. And the way it works is, if t is less than or equal to 1, then that's true, and true in APL is 1. We subtract 1 from 2, that gives us 1, and that selects the first element, which is the 0. Conversely, if t isn't less than or equal to 1, that is, it is 2 or higher, then t less than or equal to 1 evaluates to 0. We subtract 0 from 2, giving us 2, and that picks the second element. Okay, very clever. Now we have all the pieces we need for our implementation. But we're using this temporary value for the number. That's our argument. So that's omega. And what about those weights? We can compute these weights because the rule is that it has to be descending integers ending with a 2. We start off with the argument, then we get how long it is, the integers from 1 through to that length, reverse them, and increment them. And these are all the pieces we need. So we're putting together in the function. This is a check digit. So we concatenate the original digits in front of that, and this appends a single check digit to the input. So we apply that twice to compute both check digits. And that concludes our definition of the CPF function. Let's try it out. And we got the remaining digits here. Okay, but the question was, is there anything we can do to improve this solution? And yes, there is. The first thing to note here is this condition. And the condition either gives us a 0 or a numeric value. In order for us to be able to think about this clearer, let's just use some random value as the numeric value. What are all our cases? Well, the cutoff point is by less than or equal to 1 and not less than or equal to 1. So here are the numbers with t from 0 to 3, right? The cutoff is between 1 and 2. And the results, well, when the condition holds, then we get a 0. And when the condition doesn't hold, we get 42. And so there's a trick you can often use in APL. And that is when you have a condition determining whether to return a value, a numeric value, or 0, then you can use multiplication. Because true and false are 1 and 0 in APL. But for that to work, then you have to state the condition in the positive instead. So by flipping around the t less than or equal to 1 to t is greater than 1, then when that holds, we multiply by 1, and that preserves our value. And when it doesn't hold, we multiply by 0, and that, so to say, nulls out the value, makes this into a 0. If the value you want in the second case is different from 0, then there are often some arithmetic transformations you can make to make those adjustments. But in this case, it's 0 and some given value, and that makes it really simple. So we're going to stick with that, and it looks much neater. We're going to put that into our function. We can begin to see how it's getting cleaned up a bit. Next up is this whole business about the 11s. Well, let's think about what all the cases are here. So we have the numbers from 0 to 10, because after we have done the 11 residue, any multiples of 11 have been removed and we only have the remainder. So when we subtract this from 11, we get all the different cases we can get out, meaning integers from 11 and down to 1. And then we have the special rule, remember, that if t was 0 or 1, which are the first two cases here, then we need to null out those values. So we need to get 0 instead of 10 and 11. Let's keep that in mind, that 10 and 11 need to be removed in favor of a 0 instead. So we'll take that and put it up here for later. As long as we remember to adjust these two special cases, then we can make any other transformations that we want, because it's just as plain 0 as check-digit if the t is 10 or 11. So now all the cases, as I said, are anything from 1 to 11, because we are dealing with modulus 11 arithmetic, so anything else will just wrap around. And our formula is 11 minus 11 residue on these numbers. Now, because if you look at the flow of the data from the right to the left, the numbers being passed through, so to say, a filter of the 11 residue, which means that everything we do is really in 11-based arithmetic, or modulus 11-based arithmetic. So if you take a modulus 11 on the far left, we can see that the unique values from 1 to 11 are still unique, only that 11 became 0, so it, so to say, wrapped around. And that's actually good, because that's one of the special cases that we wanted. Now there's only the second case left. But let's think about this, the modulus here. Well, the rule is by modulus that you can add or subtract any multiple of the number that we're working with, 11 in this case, on the right side. So on the right side of the leftmost vertical bar, we can add or remove any multiple of 11. And it says 11 minus, which really is the same thing as positive 11 plus a negative value. So that positive 11 we can get rid of. We can just subtract 11 on the right. Okay. Furthermore, we can see that we're doing a modulus 11 twice, and that doesn't contribute anything. So we can get rid of the rightmost modulus. And so this simplifies our formula quite a bit as well. Let's put in what the actual value is rather than our test values from 1 to 11. And here's another thing we can observe and simplify. We're negating. But what are we negating? We're negating the sum of a bunch of positive values multiplied by some other positive values. Now remember in school that positive times positive makes positive, and negative times positive makes negative, etc. And so if we're summing a bunch of positive values and negating them, that would be the same as summing the corresponding negative values. Okay, we have the two factors that are being multiplied. How could we negate one of them for free? Well, let's observe. One of the two terms is a sum. It's a sum of 1 and these reversed indices. If we transform this into their corresponding negative values, then there's actually less for the computer to do, because a summation and negation are the same, and 1 and negative 1, they're just both constants. So we save ourselves a negation. It's not a huge thing, but every little bit counts. So let's put all of this together and go to the next step, which is our second special value, that for 10. And here we can use the technique that we had from before with t. But instead of doing a greater than, as we had before, we can now do it with equality or inequality, because we stated in the positive. We want to preserve the value of t if t is different from 10. Otherwise, we null it out. And that takes care of our second special case. Let's put all of this together in our function and give it a new name so we can start comparing them. We're generating some test data. Here are 1,000,000 CPF numbers. And then we can check the runtime. And notice here that we're using rank 1. This is because we have a 1,000,000 row matrix with 9 columns, and we are applying these functions on each row. So rows are vectors. Vectors have rank 1, one dimension, and we're applying these functions on each one-dimensional sub-array of the big table. And the results? That's a respectable speed up, just from moving around mathematically and simplifying our formulas. But there's more we can do. As we saw, we used rank to apply our formula to each individual row of the matrix. If you can find a way to extend our function such that it gets the entire matrix as its domain and does all the computation in one go rather than row by row, then we will see a speed up. How do we do this? Notice there's a summation of a product. Whenever you see a summation of a product, you should think inner product or a dot product. However, we have to watch out. If the function now gets the entire matrix as its argument, then when we looked at the tally of the matrix, then we're not going to get 9 digits anymore. We're going to get 1,000,000 because there are 1,000,000 records. So we have to replace this tally with the rightmost element of the shape, that is the number of columns. Furthermore, due to how inner products work, then we have to swap the arguments of the inner product so that the rows of the matrix get paired up with the vector of weights. Let's compare the runtimes of these 3. Notice here that our last solution does not need the rank 1 because it applies to the entire matrix. And this is where you really see a significant difference when you can apply a function to an entire array in one go. In fact, you can see the graph cannot even represent a relative runtime for the last solution because it's so much faster. Still, we're not done yet. For the next step, that we have optimized our core algorithm, we have to try to achieve what is sometimes called mechanical sympathy, or a way of working with the data such that it fits better with the way that the data is represented inside the computer. So let's bring it up and stare into the depth of the memory where the data resides. The way APL stores large arrays of flat data, like here a numeric matrix, is in a contiguous list. There's no marker or separator between individual rows in the matrix. Rather, the shape is stored separately, and then that is the shape is used to compute, or it is the stride to find each individual row in the matrix. And then we have on the top our vector of weights. Now, when it comes to multiplying, we can see that the computer has to replicate the vector of weights for each row. So it can apply the correct weight to each element in this matrix. And since the matrix is actually linear, it's actually one long list of numbers, then we can see we have to cycle around from -10 to -2 and then back to -10 and keep going. And while we can do this with some vector-to-vector multiplication, there's still some logistics in moving these numbers around. If we transpose the big matrix, then that means that each CPF number is stored as a column. We can call this a column store database. And each row of the matrix is then very long and represents individual digits of these CPF numbers. Now when the computer comes to compute the products, it can take one digit, which is the first row, and multiply by one number from our vector of weights. And so this allows the computer to distribute a single number, the weight, to a lot of numbers and use as wide vector instructions as are available, because we have a large amount of data. And this is going to be much more efficient. So with that knowledge in mind, we're going to clone our solution again and swap things around. So now we're going to take the data in transposed form. This means that we need to swap the arguments back again of our inner product. And since there's one digit of the CPF numbers per row, that means we are going to add additional rows instead of additional columns to our table. And therefore, on the far left, we're changing the concatenation, the horizontal concatenation, into a vertical concatenation. This has an additional benefit, because if you think about how the data is stored in contiguous form, in the old form, with one CPF number per row, adding an extra digit after the first row as an additional column would mean that the next following digit, which is the first digit of the second CPF number, would need to move up in memory one step. And so everything has to move one step more than its predecessor. That's a lot of moving around, and that's going to give an additional slowdown. Now that each corresponding digit in the CPF numbers is on a row by itself, that means that all the computed check digits are going to be added as a single row at the bottom of the table, and then when we compute the second check digit, we add another row. And if there is, and it's highly likely that there is, additional empty space in memory after where this big array is stored, that means we don't need to move all the data. We can do an in-place amendment with adding another row at a time, and that's going to make things quicker as well. Though that we're not going to be able to measure now, because we're not going to change these numbers in place. But that could potentially speed things up significantly as well. Now we transpose our data, and while that could be somewhat expensive, that's not something you need to do a lot. You just do it once, and then you work on your transposed data. Furthermore, you should really keep your database as a column database, a column store, in which case this won't cost you anything at all. Let's apply these functions each to their corresponding correctly formed argument. So the CPFB is on the row store, and the CPFC is on the column store, the transposed version. And that gave us a very significant speed up again. The asterisk on the far left here is runtime telling us that there's a difference between the results, warning us that something isn't right in this comparison. But that's only because one result is transposed compared to the other. If we were to transpose it again, they would match up. But clearly we don't want to transpose the results. Now this was for 1 million CPF numbers. Brazil has just over 200 million citizens, and if they all had CPF numbers that we needed to compute or check the check digits validity for, then that would take about 5 seconds to run. Can we do more? Well, our algorithm is probably as optimal as it gets. But now that we're computing using inner products on large arrays, this is perfect for things like GPUs to compute. And that's where compilation comes in. So this is vanilla Dyalog APL running on a normal CPU in a single thread. I wrote to my good friend and colleague Aaron Zhu, who runs, develops, and maintains the co-dfns project. And I asked him what kind of speed up could we see if we were to run this on a GPU compiled instead. And he tried it, and it's very significant actually. There is an overhead of sending all the data to the GPU and bringing it back again. And so for a relatively small amount of data, like this million numbers, it wouldn't pay off. However, if we were to compute it for all of Brazil, then it probably would pay off. And if you can keep the data on the GPU while you're working on it, then so much better. So that brings us down to 1 second to compute or check the check digits for all of Brazil. And let's say you had a graphical interface, you click a button to check things. A 1 second delay is acceptable. 5 seconds, maybe not so much without some kind of waiting, spinning thing. So let's contrast these. We went from our original formulation to something that's a little bit shorter and a little bit simpler. And that brought us from something where it would have taken 8 minutes to compute CPF numbers for all of Brazil, and down to a single second or sub-second runtime. Okay, that's great for this case. But can you take what I've been saying here and apply it in general? I'd say so. The way I've put it together here is as a bunch of questions. When you develop algorithms like this, then try to ask yourself these questions and see if there are things you can do. The first thing is whether you could use a direct computation, a formula, rather than selection. And of course, you don't want to do actual branches, where the branch predictor in the processor can get it wrong. And once you've found some kind of formula for that, then try if you can use mathematical equalities, equivalences, to simplify that formula, so there's simply less work being done. And then see if you can generalize your formula such that it can be applied on the entire set of data rather than one record at a time. And when you do that, watch out for inner products. Those are really useful and much faster than the corresponding formulations. We've shown the classic inner product, dot product, plus dot times, but there are many others, like or.and and and.equal, and so on. Have a think about the way that the data is represented in memory. And think about, what does the computer need to do when it goes through this data? And can it be expressed in terms of vectors and scalars and together with vectors and so on? Now, it can be hard to know and figure out what exactly is going on underneath the covers. Don't be afraid to experiment. Try transposing your data or various pieces of your data. Flip the axis around and see if that makes a difference. Do the runtime, and maybe you'll find to your surprise that a lot of things run faster when you just transpose your data first. And finally, if that's not good enough either, then check out the co-dfns project and see if you can compile the critical parts of your application. So those are the things that I wanted to go through today. If there are any questions and you're watching this live, then you can write those questions in chat. I'll wait a little bit to see if any questions come in. Meanwhile, while waiting for questions, have a look at this schedule. Since it's a new season, we haven't really decided what are we going to be presenting, but we will be announcing that as we go along. I'd like to point out that in a few weeks there is in the next few weeks, then there is an ongoing election, or community election of a logo, a common logo for all of APL. So check out the APL wiki /APL logo and see that there. And then on February 10 there'll be a reveal of the results to see what the community has chosen. We have a question from the chat on whether or not, if we go back a couple of steps here, this formula here, whether it wouldn't need to be changed. Oops. And it's a typo. I should go and fix that. When we go back here, we can change this to the tally like we had before, because we're storing 1 digit per row, so it should be the number of rows. My bad. We have an example coming from Tony C in the chat as well, looking at these things, and particularly about transposing your data. He says he can't agree enough about transposing that. He had an example of some algorithm where he got a factor of 3 that speed up by transposing the data. So here's a real-world example of somebody actually doing that, and with good results. Tony C also comments that avoiding branching can be dangerous, because it can be very clever but not very clear what you're doing, and that's true. Although with time you can gain experience in reading such constructs. Also, you don't need to do it if it's not something that's performance critical, of course, and something that's going to be repeated many times. If it's only a once choice between this or that, then yeah, it doesn't really matter. But don't forget to comment your code. APL is so terse that there's plenty of space left in your editor to add comments. So remember to state what the code does. Okay. If there's nothing else, then that will be it for today. We'll see you around in 4 weeks here, and then don't forget that every other week there's also a BAA session. Thank you for watching.